All right, let's try another controller right now. This is a PI controller. So the reason this controller is called PI controller is because the voltage produced is proportional to the error and also proportional to the integral of the error. So it's KPE plus KI times integral of the error. And if you want to convert this into time domain, you will notice that KP is just, KP times E is just KP times E, but KI times integral of E is going to become KI divided by S times E. So the transfer function for this controller is KP plus KI divided by S. And you can rearrange this transfer function into the following format. You can write this as sum gain multiplied by S plus some Z divided by S. So this is basically a controller with one pole at origin, which is the integrator, and one zero someplace, which is minus C. So controller with one zero and one pole at origin is a proportional integral controller, and it has some benefits. I'll let you discover that on your own when you look at the responses generated by this controller. But right now, how do we actually implement this and how do we find the gain KP and KI? Well, we are given some information. We want to make the controller 0 at minus 30. So the 0 of this controller, if you rewrite this, is KP plus KI times S divided by S. That's what this controller is. So the 0 of this controller is minus KI over KP. So that should be equal to minus 30. So that's one. And also we are supposed to make sure that the closed loop system is critically damped. And critically damped means a damping ratio is equal to 1, or that also means that the poles are real and equal. So using these two pieces of information, we can figure out what the gain KP and KI to use. And once again, these specifications are coming not from the customers. They are made up just to see how the controller is supposed to work. So here are the calculations, by the way. We take the controller kp plus ki over s multiplied by g divided by 1 plus gk, and we get the closed loop system. So the closed loop system is now second order. So with the pi controller, you are going to get, you know, 1 0 in the closed loop system, which is same as 0 of the controller, and two poles. Okay, and the closed loop 0, as just mentioned, is minus ki over kp, and the two closed loop poles would be given by this formula: minus b plus or minus b squared minus 4ac over 2a, where a is tau and b is 1 plus kdc kp, and then c is kdc times ki. And using a quadratic formula, we can find where the poles are. And if you want the poles to be equal, that basically means that b squared minus 4ac, that term should be 0, so that both the poles would be just minus b over 2a. Okay, so b squared minus 4ac term, which is this, should be equal to 0. So if you take this equation along with the fact that ki over kp is 30, because of the wherever we want the 0 of the system. So combining these two equations, like this discriminant being equal to 0 and ki being 30 times kp, if you combine these two, you can solve for the value of kp and ki individually. And furthermore, if you plug in that KDC is 1.06 and tau is 0.06, you can find the value of KP and KI gains in simulation. And here is the step response of the closed loop system, 12 times closed loop transfer function right here. And you can see the speed goes from 0, and this time it actually reaches 12. This is because of the integrator effect. Having an integrator in the forward path, having an integrator in the plant or the controller will make sure that for a step input, for a constant input, the response at the end actually matches the output. Great. And how do we code this up though? Okay, so let's do a very quick math on how to implement a differentiator. Let me first delete this, what we have over here. So the derivative, like in a PD controller or the PD controller with an extra derivative, extra filter in it. So the derivative is really easy. So derivative basically is current error minus previous error divided by delta t. But integration is going to be interesting. And then so we have that the voltage we want is kp times error plus ki times integral of the error from time 0 to t. And if you remember, what is an integral? So integral is the area under the curve. So if we have an error as a function of time, we are integrating the error overall with time. So we're finding the area. And area is could be written as a Riemann sum. So we can say that the area at this instant is equal to the area at the previous instant plus the new rectangle. So that's the logic we can use to successively find area at each instant of time. So we can say initially the integral, error integral is 0. So initially at time t equal to 0, the area under the curve is 0. But as time builds on, the logic for the area is that the area, which is the error integral at some time t, is equal to error integral at the previous time. So this unshaded region is the previous area at the previous loop time, and the total is the error integral right now. So the error integral right now is equal to error integral at the previous plus this extra shaded bit. And what is that extra shaded bit? It's E multiplied by delta t. So that's how you can implement integration. It's a running integral. Okay. And let's see that in your Arduino code right here. So in the beginning, you define all your variables and do all the setup function. And inside the setup function, I'm also setting the error integral term right now. Okay. So let's see how that. So first you calculate disk angle, do the time, differentiate to find the disk speed. Define your Kp gains, Ki gains, and Vmin. Kp and Ki we just found by theory. The desired speed is 12. So the error in the desired speed is just desired minus the disk speed. Great. And integral is equal to the previous value of the integral, which is the integral as of now, plus the error multiplied by delta t. That's exactly the implementation of this logic over here. Okay, so once you find the error integral, so this error integral is a variable which keeps on appending itself, which keeps on increasing. And every time you run the loop, the error integral becomes whatever it was, plus this extra little bit of area. So now you can find the voltage Kp times the error plus Ki times the error integral plus Vmin, convert that into DSC value, put it into limits, print time, disk speed, and disk value, and then before leaving, just update the previous angle and the previous time variables. So it wasn't that bad. So this is how you do a PI controller. Okay. After this, the data has been collected for you. You're going to run it through this MATLAB file where you define the Kp and Ki values, and then you define your plant transfer function, and then you can also find your controller transfer function and then simulate the whole system. Okay. The controller transfer function is Kp plus Ki over S. So simulate the theoretical response and simulate the actual response. And I'll let you observe, is it going to work or is it not going to work? Okay, try it out.